So if I have a system, a mechatronic system of some sort, maybe it's a sensor, maybe it's a transducer, maybe it's an actuator, I want to be able to understand how that particular system is going to behave given all the signals going into that system. I want to understand what kind of signals I might get at an output. So for example, I might have some kind of time squiggle that looks like this going into that system. I might have one that looks more like this going into that system. I might have something that looks more like a square wave going into that system. And the question is what I get here, what I get at my output here, what I get at my output right here. Right? And this would be horrific if you actually had to go through, for a sensor, for example, and characterize every possible signal that might have to go into that system so that you understand what the output looks like, and you make sure that your sensor works as you expect based on that output. So instead, we're going to do something a little bit different. So instead, I'm going to erase all of that, and I'm going to hypothesize to you that I can put one class of signals into this system, measure the output of my system, and then have a good idea of how that system is going to react to every input that I might put into that. And I'm going to say that signal, that class of signals, is the sinusoid that we talked about. Right? So I have some amplitude, some frequency, and some phase coming into this system, and I'm going to get at the output some new amplitude. So let's call this A naught, phi naught. I'm going to get a new amplitude A1, that same cosine, and this is because I'm assuming this is a linear system. So that same amplitude, that same frequency, different amplitude, same frequency, and a different phase. Right, so I have A naught cosine omega t plus phi naught going into my system. I'm going to get an A1 cosine omega t plus phi1 going out of that system. And that's, as I mentioned, because I assume this is a linear system here. And most of the systems that you're going to be playing with are effectively linear systems, at least within a range of values. Okay, and this comes from Joseph Fourier. And Joseph Fourier was actually a heat transfer guy. He was a mechanical engineer of sorts. But he basically came up with an interesting observation. Okay, Fourier observed that all periodic signals, and remember our periodic signals are defined that there's some period capital T where y of t at all time little t's, y of t equals y of t plus capital T, right? If the signal repeats itself. All of those periodic signals can be described by a constant term, effectively a DC offset, plus an infinite series of sines and cosines. And that statement should really kind of blow your mind a little bit. That's, I think, completely unintuitive to start, and the math will be a little bit unintuitive as we go through it, but hopefully you'll be a little more comfortable thinking about this by the time we get to the end of these Fourier series and Fourier transforms. But the basic idea that I can represent any, in this case, periodic signal, and you'll see in a later lecture how I'm talking about any signal by this infinite summation of sines and cosines is truly mind-blowing. So let's get some sense of what's actually going on there. So here I have a square wave, right? This is pretty clearly a periodic signal, and I can actually measure the period here. So if I go in here and measure this distance, that's defined as my period from this rise, this low to high step of the square wave and this low to high step of the following cycle. And if I go in here, I find out that I had set this at 2 pi seconds. Right, so my units of this are seconds. And using that period, I can actually go calculate a frequency, for example. So my frequency is going to be 1 over t, which in this case will be 1 over 2 pi cycles per second, so in this case hertz. And then I can also think about a cyclic frequency, or omega. So omega is going to be 2 pi f, remember that's my circular frequency, and I will get 1 radian per second in this example. So this is a square wave, it's periodic, and so what I just told you is that I can represent this square wave by a constant term plus this infinite series of sines and cosines. And so let's start actually playing with that. Okay, so here's my first attempt, and of a single sinusoid. Okay, this is a single sine term, but I've written out the full thing to be a little bit more complete. So I have a constant term. In this case, this is my DC shift or my DC offset. This A naught is my constant term. And then I'm going to have plus a bunch of cosines and sines, right? So I just started with the first of those terms. So A1 cosine t plus B1 sine t. And I'm doing this in a slightly confusing way, and so I apologize for that for some degree. This is effectively 0, right? Because I'm only plotting this sine term, but this is what I need to actually kind of complete this infinite series of cosines and sines, and you'll see where this comes in a bit. And then I also want to explain my choice of frequency here. So in this case, I used a sinusoid that has the same frequency, that omega equals 1 radian per second, as my square wave. And this is generally going to be the case if I have a periodic signal. The period of that signal is going to define what we call the fundamental frequency. So in this case, this omega is 1 radian per second is going to define my fundamental frequency. And I also have some coefficient on that term, and that's defining the amplitude of the sinusoid. And we'll get to how I actually ultimately calculate that amplitude in order to plot this a little bit later on, but this is the first step, right? It's certainly not a square wave, right? This green line, this green curve is not a square wave, it is a sinusoid. But let's see how we can improve that and make it something looking closer to my yellow square wave here. So I've now added 4 extra terms to this equation of approximating y star, so that should be y star of t. Right, and I have my constant term, still my cosine and sine with that fundamental frequency of 1 radian per second. And now I have 2 more terms effectively here at a frequency of 2 radians per second and 3 radians per second. So I'm basically just using integer multiples of that fundamental frequency for my infinite series of sines and cosines. Right? And these have their own coefficients associated with them that are scaling effectively the amount of the cosine or sine at that frequency that's going into building this signal. And so this blue signal now is what's represented by this term, and to be quite honest with you, still we have a lot of 0 terms in here. So in fact, all of the cosines are going to be zeros, and this 2t term is also going to be 0. Right? And I can certainly explain these top ones, the fact that all of the cosines here are 0. Right? And there's an interesting feature of this square wave signal as I've drawn it that makes that the case. Right? So my square wave is what we define as an odd function. So that means that an odd function means that y of t is equal to negative y of negative t. And so that means basically I can flip and over the x-axis and then over the y-axis. So if I downshift this to 0, I can see that I can do that, and it's an odd function. A sinusoid in general is an odd function. A cosine is an even function. And an even function, y of t is equal to y of negative t. It's effectively reflected around that y-axis. And so because I have an odd function, my kind of infinite sum of sines and cosines that are creating this, I'm really only going to use the sines in order to do that. If I had an even function that I was trying to represent, then I would use the cosines only. And obviously if I have some arbitrary function that's neither even nor odd, then I need both those cosines and sines to represent my function. Right? But we've also just taken this one step further, right? This blue line definitely looks a little closer to the yellow square wave, right? It has slightly steeper edges here. Not this single point on top. It's still fairly lumpy on top. But it's definitely steeper in the edges, and so that's getting me a little bit closer to my square wave. Right, and I've added even more terms now. I've gone up to 5 times that original frequency. So now I have t, 2t, 3t, 4t, 5t, right? And it's getting a little bit closer, right? These edges are getting a little bit steeper in this purple curve here. This is getting a little bit flatter potentially. Right? And if I keep doing this, right, if I make this an infinite series, and I go up to these really high frequencies, then I will get an actual version of that square wave if I go all the way to infinity in my summation. And one other definition, in addition to the fact that this kind of base, this lowest frequency, other than obviously the DC component here, this lowest frequency term is called the fundamental frequency. All of the other terms here are going to be called the harmonic frequencies, or harmonics. Okay, but I can also represent this in a much more compact way. Basically, the description that I gave you earlier, where Fourier said that we could represent all of these periodic signals by a constant term plus this infinite sum of sines and cosines, I can write it explicitly doing exactly that instead of listing out all of these terms that I might have. So in this case, my y of t is going to be equal to that constant term, a naught, plus an infinite sum. So I'm going to go from n equals 1 to infinity. And then I'll have my cosine terms, and I use a coefficients for those, so a sub n, and then cosine n omega naught t here. And I want to point out that this omega naught is our fundamental frequency. Right? And then we still have our sine terms, so we use a b coefficient for those, so b sub n, and then sine n omega naught t right here. So that omega naught, once again, is going to be that fundamental frequency. And anything over n is 1 is all going to be my harmonics. So when I have 2 omega naught, 3 omega naught, 4 omega naught, so on, are all going to be harmonics of that fundamental frequency. But this, of course, this expression right here is now providing me a description of, once again, any periodic signal with this infinite sum of sines and cosines. And now, of course, the trick is actually going in here and figuring out what all of these coefficients are, right? And we came up with some simplifications for example, for an even signal, all of my sinusoid terms would be 0, so all of the b coefficients are 0. If I have an odd function, all of the a coefficients are going to be 0, at least a greater than 0, so a1 through infinity coefficients are going to be 0. Right, but let's look at a more general case of how we would actually compute these coefficients in the next lecture.